start. Now then, so this nice intimate group of people give me great pleasure to introduce Byrne, and you can read all about him in the programme. I believe he's going to talk about wind turbine and wind energy. So with no further ado, over to you.
Thank you. Let me just start my timer so I can make sure I stick to time. I'm going to talk a little bit about offshore wind, a bit of an overview, talk a little bit about the ambition in the UK and the work we're doing in Oxford and how it's contributing to the direction of travel, hopefully fairly high level. So that's me. And obviously this is what I'm interested in, the offshore wind turbine. Big farms of them that are being installed around the UK coastline. I thought I'd start with this slide, which is for offshore wind. And obviously there's a big sector which is onshore wind. I'll touch very briefly on that. But this is a plot I've made about the UK ambition for offshore wind. And in black, that is our current position of where we're at. And you can see that installed capacity is about 15 gigawatts, starting from about 2001 with 2 turbines in flight. I actually started doing work in this area in about 1998, so I've seen the whole thing develop. I've also put here, this dash line here is wind farms in construction, maybe about another 4 or 5 gigawatts of wind farm, and then the ambition. This is what is consented to be built, and almost certainly likely to be built in the next 5 to 10 years, I think. Many of these wind farms are being designed as we speak. There are engineers working on it. It's a big ambition, and so we expect to see rather large numbers of these turbines being installed. You can see actually here, for the first 15 gigawatts, 2,800 turbines. The next 15 gigawatts, about 1,100 turbines. So the size of the turbine getting bigger and bigger. Actually, the first one's around 2002, maybe 2 megawatts. Current generation, about 9-10 megawatts. And in the future, maybe 15, 20 megawatts. Where are they being placed? Well, you can see this map of the UK. The original first generation wind farms close to shore, not very many turbines, not much power being generated. With more experience, further offshore, bigger wind farms, now getting to the size of the 1-2 gigawatt wind farm, which is essentially a power station distributing power back to the UK. Just for reference, I looked at the National Grid dashboard this morning. Demand in the UK is around 30 to 32 gigawatts. You can see wind turbines, 15 gigawatts, obviously not 100% efficient, maybe 40% efficient. So perhaps contribute 7.5 gigawatts to the national grid. Onshore, there's another 15 gigawatts, so probably contributing another 7 or so gigawatts. But clearly a bit intermittent with time. So this morning, I think we was contributing about 2 gigawatts, whereas last week or week or so before that, it was contributing about 14 gigawatts. So it varies in time. And of course, the ambition in the UK is matched by ambition in Europe. All countries have big ambitions, many tens of gigawatts of power to be developed, not only in Europe, but the US really going great guns, China, Japan, even Australia, everywhere around the world, they see this as the way forward. Known technology, the key question is about the engineering. So it is a multidisciplinary problem. All the different areas that are involved. We've got design of the blades, the generator, gearbox, the dynamics of the system, loading on the structure, the design of how you anchor it to the ground, which is what I'm most interested in, how you get the power to shore, how you store. I mean, storage is going to be the key problem for the future. So it's a multidisciplinary problem. Requires very skilled people, actually. And I think that's one of the areas that I'm going to touch on at the end. That for this sector to develop, really we need more skilled people, skilled engineers. There's a huge ambition. You've got to build, if the UK is going to build 1,000 structures in the next 10 years, you've got to design each of these structures and multiply that across many different countries. You've got to have a very skilled workforce, and I think that is an area which is likely to slow down development. So, basic engineering of the problem. This is the scale of the problem, just to give you some perspective. And I've got here some Oxford reference points, Magdalen Tower, Engineering Tom Building, about 42 metres, both of them. Christchurch Tom Tower, I found out this morning, is 45 metres. So those are the local reference points. This was the turbine being built 10 years ago. This is probably the current turbine. And this is where we will be probably in 5 years. We're designing this right now. And it's all at the right same scale. So you can see this is it's a massive structure. The blades, 110 metres long, have to be properly engineered. These structures have to last for 25 years at least. And in the offshore environment, sustain pretty heavy loads from the waves. You can think in the North Sea, in a storm event, might get a wave that might be 25 metres high. The height of this building is 25 metres. And so that might be an impact that these structures would have to survive. And at the same time, they've got to be generating electricity for the 25 years, or as much of it for the 25 years as possible. So they'll always be rotating. Except, of course, in big storm events, they often will stop rotating just to reduce the load on the system. So I put here, structure, simple structure. The tower, for example, of these future ones will be about 15 metres in diameter. I think that atrium area is probably less than 15 metres in diameter. So you think the scale is impressive. So these are the sorts of structures that you could go for. In Oxford, we have been working on all of these different structures over the last 25 years and would be recognised as experts on all the different structures. The most common structure is this one, which is effectively a large diameter steel tube that you hammer into the ground with a large hammer. Most wind turbines sit on this sort of structure at the moment. It's pretty cheap to make, easy to install, very robust. There are other sorts of designs. So this sort of structure is what might be referred to as a upturned bucket that you sit on the sea floor and you effectively suck into the ground. So you have water in the inside of the bucket, and you pump that water out and it forces it into the ground with the pressure of the water on top. So it's actually very attractive because it's easy to install and effectively noiseless. These sorts of structures are where we're heading in the future with deeper water, the floating structures. Much more expensive to make a floating structure. But actually, as you go to the bigger turbines, the cost of the support structure as part of the overall cost becomes lower. And so the economics for floating structures becomes much better. And of course, for deeper water, for areas like around Japan, maybe some parts of the US, you need floating structures. And even in the UK, in Scotland, there's the Equinor High Wind project, which is in about 100 metres of water, which is a floating system. So I'm going to talk briefly about Oxford work, just to give a flavour of the sorts of things we are contributing. Our focus is on this main support structure, which is effectively a large steel tube. And you might think that's a very easy problem. What we want to know is, here is the steel tube. It's a pretty simple problem. I mean, many of you will have seen a fence post, and you want to know how much force will the fence post take before it falls over. Same problem. We want to know if we apply a force to the tower, the turbine, how deep do you need to push this steel tube into the ground to support the structure? And here are some designs. This is a 7.5 metre. So this is almost a historic piled foundation. Here's a person. So they're quite big. Here's a pile driving system for offshore. So they have these big hammers that just bash this thing into the ground. So it's quite a simple structure. We do a lot of modelling of these structures, so I won't go through the detail of that, but we have computer models of the structure where we model the effect of the blades and the rotations and the dynamics of the system, because these are quite slender structures. They can vibrate and flex, and you can imagine if something's turning at maybe 3-4 RPM for 25 years, you can see the thing vibrating around. So we're interested in how deep does it have to be, and what's the diameter, and then also what is the wall thickness. You might say that seems like a pretty easy problem, and when I talk to people, they say that's a pretty easy problem. Yeah, maybe it is a pretty easy problem, but you've got to make sure that after 25 years the thing hasn't fallen over, and that's what we're mostly concerned with. And the other thing you need to make sure is that it hasn't vibrated itself to a fatigue failure. So about, it's now 8 years ago, I can't believe it's that long ago, I started a project which is called the Pisa Project, which was funded by most of the developers in the UK to develop new design methods for these foundations. It ran for 4 years, cost about £4.5 million. It was multifaceted. It involved a team in Oxford and a team at Imperial College, which I led. And what we did were, at the core of it, scale model tests of these foundations. And unfortunately, the video doesn't show, but we were able to load models of these foundations together to understand how much load they could take. These are 2 metres in diameter. So these are still scale models of the big thing, but you need to do it at that scale so that you get confidence of the design calculation. We also did a lot of new computational work using advanced engineering calculations, and then produced some simplified calculations for the engineers in industry to use, and they can produce their calculations. This was a very successful project, and actually we published all the work. It's available open access. There were 10 developers involved. They got all the reports. Carbon Trust was involved as a sponsor as well. So it's been disseminated to all of the main players in the industry. It's won some awards. It has also been applied to a number of wind farms. So it finished in 2018. Hornsey 1 came on stream as an operational wind farm in 2020, using the design methods for the design of the structures. And I'm pleased to say that the Hornsey wind farm is still operating and there's no failures. So at least the system works. But since this time, it's been applied to at least 10 wind farms around the UK, a number of wind farms around the US, and is the standard method for designing structures for offshore wind at the moment. So moving forward, we have, starting at the end of that project, I agreed with Ørsted, who are one of the main developers in the UK, a sort of follow-on project, which only involves Oxford, but involves developing these design methods to the next level. So the previous project, what we were able to do is really cut the cost of the steel work required by a really quite substantial amount, and optimise the support structures across a wind farm. So if you have 100 wind turbines, you can optimise each of them individually as part of the design process. Now, these design processes occur very quickly, so you need fairly quick calculation methods, and this method achieves that. So now we're moving on to the next phase, which involves looking much more at the detail of the loading that is applied, and in particular the fact that you get repeated loads all the time. And we see that there's a potential to save even more money by accounting for that in the longer term design. And we have a number of different themes of work, but at the centre of it is a large program of, again, scale model field tests. We finished one set last year. We've got another set this year. This project is costing about £7 million. The final point I'd just like to mention is the Centres for Doctoral Training, which we're involved in. We've been involved in 2. This, I think, is very important for the university and for the industry. It's about creating the next generation of leaders. And I really feel that in the renewable sector, there is a real need to boost that number of people going in, because if you're building a large number of wind farms, you need people who are skilled enough to take the leadership roles that are required to take it forward. We have a significant industry engagement with most of the main players, so that, and many of the people on this slide are now finished, are now working for these companies. So I'm going to finish now and hand over to Henry, but clearly offshore wind is a main player in the renewable future. We can do a lot on the engineering side to optimise things, and Oxford is leading a lot of that work, and also the training of the next generation of leaders. So I'll pass to Henry to talk about PVs, and then happy to take questions at the end.
That was very interesting. And yeah, we're going to have a little time for discussion at the end, but I'll go straight on. I need to time myself to make sure I don't go over. So I'm going to be talking about solar PV, a little bit of sort of general aspects, and then talk to you a little bit about what we're doing in Oxford, some of the activity we've got going on in the research and the industrialisation from Oxford. So you all know, you've probably seen this morning, and you're all aware of the different sort of projections for carbon emission and their influence upon temperature rise. And what's clear is that in all these projections, this is just some data, world data, lots of these projections lead to certainly uncertainty, but risks of going above the sort of 2-degree pathway. And in fact, if we want to get to 2 degrees or 1.5 degrees, we clearly have to make a massive transition to zero, in essence, practically zero carbon production, or offset by carbon capture, at least over the next few decades. You're also aware that renewable energy technologies are rapidly coming down in price. We've just seen that on wind, onshore and offshore wind. Solar PV is certainly no exception. In fact, arguably the most rapid reduction in price of all technologies. So there will have to be changes, but this can also be an economic benefit, this transition to renewable energy. And solar, in my view, solar and wind can pretty much do the majority of the share, and they obviously balance each other quite well. It's actually reasonably sunny today, there's no wind. So if we had 30 gigawatts of PV installed in the UK, we'd be producing a fair amount of electricity from that today. So globally, looking globally, what do we have to achieve if we wanted to produce most of our power from PV? And whether it's 50% or 100%, it's sort of almost in the noise, if you like. Obviously, it has a massive impact on the carbon generation. But this is the historic growth over the last decade, 2010 to 2020. And simply keeping the growth at that rate up until sort of the mid-2030s would actually have enough production capacity over the subsequent 25 years, which is the lifetime of a typical solar array, or at least the expected useful lifetime, to reach 80 terawatts peak of PV power. Now, PV, that doesn't mean we've got 80 terawatts of electricity. Probably, depending on where they're deployed, it's something like 20 terawatts of electricity, but that is our global energy demand. So it's not infeasible at all to think that these technologies of photovoltaics could do this. Of course, we've basically got to sustain the historic growth over the next period of time to enable this. So how is the growth, why has the industry grown so much over the sort of historically? Of course, early on it was due to subsidies, and then more recently it's been just simply due to the economic cost reductions of solar. This has been partly due to scaling, partly due to improving the efficiency of the modules as well. So most of today's installed PV, over 90%, probably about 95%, is silicon, based on silicon wafer technology. But that is not just one technology. There's been generations of different technologies that have come through. that have been increasingly efficient and increasingly stable, has been driving the cost reduction. If you look at how do we keep driving that cost reduction with silicon? Well, if you look at a module, it's made of multiple components. The cells are in the middle. They're laminated between two glass sheets, and there's a junction box. Typically, the cost of the cell, it's sort of hand-wavingly, it's not precise and it depends on the technology. Cost of the cell is about half the overall cost of the module. So you've got about equal cost of cell and module. And so if you want to make the whole module cheaper, if you reduce the cell cost, you're only attacking half of that cost. And of course, the deployed modules at utility scale, the cost of the overall PV system is about twice what the module cost. So half that cost is on the deployment balance of systems. If you look at domestic rooftops, the deployment costs are about 4 times what the module costs are. So all in all, if you come back to the cell cost, it's somewhere between a quarter and something like an eighth of the overall deployment cost of PV. So even if those cells were free, you couldn't massively reduce the cost. You could drive it down further, but it's sort of with diminishing returns. Whereas if you can increase the efficiency of the cell, this has a direct sort of almost linear improvement on reducing the cost. So the question is, how can the cell efficiency be increased? And of course, this has been one of the strategies that's been successfully deployed in the industry, going from different silicon technologies and improving it. But there is ultimately a brick wall thermodynamic limit, and then there's a practical limit that takes it back a little bit further. It's very unlikely to get PV modules beyond 26% efficiency, and it's arguable that manufacturable PV cells with a single junction, so a single solar absorber material, will ever go beyond 26%. So what can we do to move this further? And this is related to the work we're interested in Oxford. And one technology that as a concept is relatively old, and it's used in concentrated PV cells, is to go to tandem cells or multi-junction cells, where multiple layers of different materials are stacked on top of each other. Typical materials used for high efficiency tandem cells are 3,5 semiconductors, materials like gallium arsenide, gallium indium phosphide. These are generally grown by sort of molecular beam epitaxial growth that is very slow and expensive. So it's what's used in space grade applications, but it's not useful for terrestrial applications where we want it. It has to be at least as inexpensive as silicon, which has become the manufacture. So what we've been looking at recently is different materials and different concepts that can deliver tandem cells and deliver fundamentally more efficient materials. And this is where we come to metal halide perovskites. Most of you probably heard me talk about these materials before. The perovskite material is a material that adopts a specific crystal structure. It's this little inset here is a schematic of the crystal structure. And the materials that are good for solar technologies are based on lead or tin halides so it's a 3-ion system. It's a 3 components in there, and they use an organic positively charged ion or a small alkali metal ion as one of the components as well. So these materials make the solar absorber material. This picture here is a cross-sectional electron microscope image just to illustrate a device. This is a transparent conducting oxide, fluorine-doped tin oxide, or indium tin oxide. Contact layers this is a very thin layer of tin oxide that ensures that electronic charge just flows in one direction. And then on the other side, this is the perovskite absorber layer. On the other side, we've got a whole p-type material and then a metal electrode. So within Oxford, there's lots of research on developing and understanding how to grow these materials, trying to find new absorbers based on these materials, trying to integrate them into devices, understanding the fundamental sort of photo physics and charge carrier dynamics inside these devices, and understanding how to maximize the efficiency and performance and what limits the efficiency and performance. But coming back to how does that material by itself deliver something better than silicon? In principle, not. One of the reasons why it may do is because it's much thinner. It's like 1 micron thickness rather than a few hundred microns. So there's less material. Also requires less energy actually to produce. these materials crystallize at 100 degrees rather than a few thousand degrees. But back to the real challenge of how do we make more efficient solar cells. There we want to make these multi-junction cells, and there actually the perovskite can be tuned to perfectly match silicon, and combining perovskite on silicon actually leads to very high efficiencies. These PCE stands for power conversion efficiencies. These aren't real numbers. These are numbers we've calculated for different types of devices. This, for example, shows the spectral region. This is wavelength of light. It shows the region that one cell will operate on and the cell behind. And if we could make cells like this that stack on top of each other and operate in different regions, we get up to nearly 34% efficiency. That compares to the 26 that we think is the practical limit, 26, 27 practical limit for silicon. And of course, going to further junctions, triple junctions can get up to higher efficiencies. So a lot of what we're doing in Oxford is trying to work out how do we make these different perovskite materials with the different band gaps that they absorb over the solar spectrum, and how do we maximize the performance of these individual junctions, and then how do we fabricate cells and layer them so that we get these multiple layers all being able to be deposited on top of each other. In terms of efficiency, this is a bit of a busy sort of chart. This is a zoom in on a region of the so-called NREL efficiency chart, so the National Renewable Energy Laboratory in the US keeps up to date an efficiency chart. And all these different lines represent different technologies. I mentioned these 3-5 semiconductor-based cells, single junction gallium arsenide, still the record efficiency for a single junction cell, multi-junction cells with these 3-5s, it's sort of up to 33%. So these are the sort of efficiencies I've been theorizing for the perovskites, but actually the perovskites aren't that far behind. Basically 30% efficiency for perovskite on silicon, and still plenty headroom to move beyond. And notably, it's with a sort of manufacturable technology. Going beyond this, I mentioned these triple junction devices. These are just some examples of some cross-sectional images of what we call an all perovskite triple junction. So these are 3 thin film layers of perovskite on top of each other, absorbing different regions of the spectrum. And then this one, this pyramidic-like structure here, this is silicon with 2 layers of perovskite. So this is going to be the next generation of technologies, and we're working on enabling these by having the right material choices for all these different layers. They have to be electrically interconnected. They have to be fully transparent below the absorption band of each cell, so all the rest of the light goes through to the subsequent junctions. And there's a lot of engineering of the electronics and the interfaces to make sure they're reliable and stable as well. So as well as the academic work and this will work on trying to understand the basic science, we've been involved in trying to industrialize this technology for a spin-out from the physics department, Oxford PV. It's got 2 bases. The headquarters is in Yarnton, just north of here, where lots of research and development is done. Basically, the company takes the technology we've developed in the university group and then tries to make it industrially compatible, stable, processed by manufacturably compatible methods, and then transfers that across to the pilot production line that's been established in Germany, in Brandenburg. These are just some examples of the efficiency improvement over time for these tandem cells, perovskite on silicon from Oxford PV. And then this is just illustrating one of the challenges. So in the university group, we made 1 centimeter squared cells. That's a large cell for us. The companies had to make full wafers, obviously, the normal format. These are the sort of M2, M4, M6 formats for those who know about silicon, and then integrate them into modules and do the modularization. Well, there's a little video on there that's actually working. I thought that's the perovskite layer being deposited. It's as simple as that. This is the layout of the factory. I mean, it's very much first of a kind. It's not going to make any impact to our global climate from this factory, but this is a proof point to then scale up to multiple gigawatts and beyond this technology over the next period of time. And this is a spec sheet of what the targeted product is. You can't buy this yet, hasn't been made yet, but the company's rapidly approaching this being the first product. Sorry, it's turned into a sales pitch, which it wasn't meant to. There's quite a lot of activity elsewhere in the world on perovskites. Certainly, thousands of researchers working on it in university groups, but also quite a lot of industrial activity. These are some startup companies in the US, Poland, China, and then there's also sort of large industry, and this is by no means an exhaustive list. Electronic companies who are active, trying to pursue different types of applications. Should also point out, Swift Solar is a US spin out that is trying to commercialize not the high efficiency tandem product, but lightweight and flexible foil for buildings or for aeronautics. And actually, that was founded by a collection of PhD students and postdocs from my group, which I sort of encouraged them, but obviously they're now potentially competitors, although I think it's quite a complementary area. Saule Technology is a Polish company. Actually, one of my PhD students is also one of their chief technologists in that company. I have spoken to him over the last few years, but not often, but they're working on flexible, lightweight stuff for buildings as well. So trying to apply this technology to different applications. And of course, in the future, in the near future, we want to be generating power from any surface we can, so that we can produce power where it's used, as well as centrally and then redistributing. The value is obviously higher if you can produce it directly where you use it. So with that, I'm going to stop myself. And so thank you very much. So now we will open the floor up, open the panel discussion. How long are we meant to have?
We've got till 20 past.
Yeah, so we've got a little bit of time.
Discussion or questions?
Yeah,
or...
yeah.
Can I ask a question about the upfront discovery, innovation and research, how big that is compared with the money that needs to be spent downstream to turn that into a scale business? Do you have a feel for the relative sizes of those two spends in both advances in wind and advances in photovoltaics?
You go first.
I mean, I don't work in isolation of the rest of the world, so there's been a lot more activity spent externally as well, a lot more money externally. Within the sort of activity in Oxford on perovskites, as an example, up until the point at which we founded Oxford PV, we probably spent about £5 to £8 million. To date, there's probably been £30 million in grant funding invested in that upstream R&D, sort of discovery area. In the company, there's been significantly over 100 million invested so far, and it's going to take certainly probably another 200 million to get to production. So you're talking at least 10 times, and that upstream research has been quite broadly spread in terms of what it's trying to enable. You're talking about at least 10 times the spend, in my experience, downstream. And possibly we've been quite focused and successful in the upstream side as well. So you might be, I don't know, you might be talking about a bigger ratio.
And can I subsidiarily ask, did it have to happen outside of the UK that bigger investment took place?
So the investment in Oxford PV has been, it's been global investors, but the money's come into the UK initially. Oxford PV set up the pilot and first production line in Germany. That was based on opportunity of looking at available sites. So that didn't have to happen there. It was a choice made on looking at available sites that were present. So we looked in Europe, primarily Germany, in the UK, and also in the US. And there happened to be a thin film small factory that was previously owned by Bosch, still run with a lot of equipment and facilities that they were looking to get rid of. So it was an economic purchase and an actual running facility. So it saved time of building a new site or setting up all the infrastructure, and we could repurpose a lot of the equipment. So that was opportunistic. As for the manufacturing line, the larger scale, gigawatt scale manufacturing line, that really could be, it's most likely to be in Germany or the UK, and that's not signed, sealed, or delivered by any way in terms of where that would be. It'll be where it's most cost effective and where the best support can be received.
I think it's a bit more difficult because it's not a business. What we're doing is improving design methods. But the first project I talked about cost about $4.5 million. There were 10 partners, and it had some money coming in from the Carbon Trust. So you could imagine that each partner put in maybe a tenth or less. Using the method it saves around, for one of the foundations, 30% of the steel. Typical foundation at that time would weigh around 1,200 tonnes. So you're saving a very substantial amount of steel per foundation. Hornsey Wind Farm had 174 turbines sitting on foundations. So you get savings of steel, and you also get savings in the vessels you need to transport the steel and install. So there's a more indirect savings. So you could imagine actually within the first few structures, you've already covered the cost of the research. I should say it is highly unusual for a research project that goes from 2014 to 2018 for the results of it to be actually used in a construction in 2019 for an operational wind farm in 2020. It's almost unheard of. I mean, I've not heard of it before. And the reason it got fast-tracked is because all the developer partners were involved in the research. We must have had 6 or 7 workshops with all their technical experts. So probably 60 people in a workshop discussing the work as it proceeded. They could feed in. We also had the certification agencies involved as well. So they basically signed off on the design method as it was being developed. And the other thing that we did was that we deliberately did not try to change the way in which calculation would be done in the sector, but improve the way in which it would be done, if you see what I mean. Not introduce a new calculation method, but actually say, this is what you do already, and if you increment it in this way, it would be better. So it's sort of, it wasn't a change, you see what I mean. But calculating the saving was huge amounts of savings.
To me, it leads to the question of how we apply ourselves accelerate. So it's like overlapping, don't do things sequentially, move to the next phase and so on. So, I mean, to me, that's a challenge to people coming together, is how to make the things just compress.
I think
faster.
What you need is to make sure in a project, I mean, in this project, we deliberately got the developers together. There was a mechanism by which they supported research, and they accepted the people involved were good at what they were doing. Research could then be applied. And I think that's what you need. And then you need money.
Yes.
Yeah, I have a question for each of you. Let me start with Henry, since you were just speaking, Byrne. Henry, just briefly, is working with Junction and Brandenburg, has that been screwed up by Brexit in any way?
There had to be a bit of contingency put in place for sort of materials and shipping things and supplies on both sides, that you couldn't rely on such quick necessary sort of transition, sending things across from one side to the other. So there's a bit more of an inventory built up on either side, just to mitigate
paperwork.
It's pre-production at the moment. I think that once into actual manufacturing, that's when the impact of Brexit and location, and it's certainly Brexit will feed into site selection and choice, and there's some potential benefits of being in the UK, but there's obvious benefits of being in Europe as well, being within the single market.
The market, the more sunshine.
Absolutely, right away. So that might be, there might be the risk of not being in that large market for the first, for significant volumes, is too high to take to make the decision to be in the UK.
I had a question for Byron. This is an unfair question because you work on foundations. But I wanted to ask you about floating wind farms. Can you tell us, somehow sort out for us between the hype and the reality? I mean, the people who like them are very, very upbeat about floating wind farms.
I have worked on floating, and I'm part of the Supergen Offshore Renewable Energy Hub, which is focused on floating. I think that there is still a very significant amount of nearshore shallow water sites that can be exploited. And so it's clearly cheaper to do that for various reasons. Equally, there are some areas where you can only use floating. I think a floating structure is extremely difficult to manufacture cheaply, but there are sort of experiences being gathered because there are some pilot studies like the Equinor high wind development. So there's experience becoming available. And as you move to the bigger turbines, the cost of the support structure becomes less critical. So I think it's the sort of thing you can see in 5 years' time as being, almost that's where we need to be. And a lot of people are working on it right now.
So I noticed that high wind, which for those who don't know, it's the only sort of existing floating wind farm. It's been working with very high load factors. So there must be some compensation between getting into better wind resource areas and the cost.
The cost of I don't know the exact numbers, but it's a very considerable cost for that wind farm. But you're right. The advantage of floating is you can get them to areas where the wind resource might be much higher. You have more efficient devices. You've then got to trade that off against the cost of the support structure, and clearly, anchoring these systems. You don't want to go too deep because you need more, cables. so there's going to be that trade-off. But you can imagine the sort of 100-meter water depth as being the ideal location for a floating wind farm. And if you get to a 20, 25 megawatt turbine, I think the economics there is going to start really adding up properly.
Straight at the back there, please.
Hi, Arabella from ACOGE. I have a question for Byrne. So I'm gonna start my question with sharing my previous working experience back in China.
Sure.
So this is a question about onshore wind. So in recent years, there has been increasing of people's concern about environmental impact that onshore wind could bring to resistance. So and we've seen some cases in China that the local government, because there are so many resistance coming from the people, and they're saying, complaining that ever since we have this wind farm in our region, and the animals coming out of the mountain and then scared us, the snakes or whatever, and the wind turbine when they're floating, and it creates noises and really impact our lives. And also and the air pollution has increased because the wind farm is here. And so because of that, we've seen the local government has been put out projects, wind farm building projects. So I want to ask you, can you share some a successful international experience of preventing or reduce people's concerns in terms of that? Is there any I think the China can draw on?
Difficult question because it's all about perception. I think in this country there has been concerns about onshore wind. But at the same time, there is a lot of onshore wind in the UK. It's almost the same as offshore. I think I think it's very difficult to change people's view of what an onshore wind farm is like. My own view is that there may be sites where you can develop onshore wind, which is close to a town and allows easy distribution of power. That may be an advantage, but actually the advantage really should be looking offshore. And the reason is, onshore, you are very limited to what you can build. And what I mean by that is there's only so big a structure you can transport on the road network. So basically an onshore wind turbine is limited to about 2 megawatts maximum, because the tower you can't transport. Offshore, you're unlimited pretty much, because we can transport very big structures to the site. So you can get to your 25, 30 megawatt turbine. And then the economics really kills is really very good. So I think it's very difficult to answer the sort of the perception question. Actually, where we should be going is, where there's a need locally, maybe you look at onshore wind, but actually it should be offshore. I should say that the town I come from in Australia, which is a very remote town, has had an onshore wind farm since 1980, powering the town, sort of defraying about 30% of the town's electricity supply from onshore wind as opposed to diesel.
From a Chinese perspective, is there enough offshore resource, or do you need to have onshore wind turbines?
Because we have a large territory, we do have a great amount of onshore vintage in the mountain. But the government, so we've developed offshore wind energies so far, and the central government now is planning to do more research on and dig out more resources and energies, more far offshore wind resources. Yeah.
We have a question about just behind, right at the back, sorry, and then we'll come forward to you.
I have a question for you, and it's kind of along these lines. So PV has obviously fallen in price, and the perception by the public was always very positive. And we have only silicon on the roofs, which has very abundant materials and non-toxic materials on. But coming to Oxford, I was running into two strange conversations where I suggested, we discussed installation of solar, and I was told, but it's not just yet there, and it's also toxic, or there are some problematic elements in there. I couldn't quite understand which elements they mean. But of course, with you and Oxford PV in Oxford, and these kind of tandem devices taking off and reaching really these high efficiencies, how would you address the public with the toxic element in your panels? And
there's obviously a push to make things ecological as possible, and there's a large push for eco-labeling as well, which is something that from the new technologies coming forward, they're certainly going to be pushed to be eco-labeled. And this relates to the overall understanding, the overall full life cycle assessment of the technology and of the product, and what's the environmental impact on multiple factors, including carbon, including social. There's multiple different categories that any manufactured technology basically needs to be assessed by. In terms of environmental impact from PV panels, it's primarily the energy that's put into making the silicon. And it's primarily that is predominantly produced from electricity produced from coal-fired power stations. So that there's a carbon sort of quota, or carbon, you can quantify the amount of carbon that's got in related to that. And that's the main driver for the sort of the carbon footprint of PV. But it's the carbon payback, which is basically more or less the same as the energy payback, is something like 9 months for a modern PV panel. So it's more than offsetting its negative environmental impact collectively over the time of deployment and manufacture. The new technology like perovskites has a lower embodied energy because it doesn't take as much energy to produce the raw material, and it's producing more power. But the material, our materials contain lead. And of course, lead is something that people know has a toxicological impact. The way to address that is to do, again, thorough life cycle assessments. And certainly lots of people are doing this. We've done this, and assess the overall environmental impact of lead under different scenarios, whether it leaks into the environment, etc. And the reality is there's actually a very small amount of this material. So even if it completely leaked into the soil underneath the panel, you'd still have a much lower content than would make sort of lead to concern of the soil. So there's specific levels of different elements you're allowed, and specifically lead in the soil, for instance, before you can't farm on it. And it would be, only a few percent of the content from leaching all the lead into the soil, then you'd have to be concerned about not being able to farm or produce food. So it's a very small amount. But the public perception needs careful sort of control and tuning. And it's all, in my view, it's all about being upfront about what's in there, the mitigating strategies, the actual impact, and having a lot of scientific evidence. And it's not just the public, it's also legislation. As you know, at the moment, PV is is not subject to ROC, restriction of hazardous substances. That is the case for most electronic goods. But this gets assessed every 4 years or so. A silicon panel has a lot more lead in it than a perovskite panel because it's used in the solder. To get the 25 years plus, you need some lead in the solder for standard PV. So almost all the panels that we're deploying in Europe have a fair amount of lead in the solder because it's needed for longevity. And that's why they're not subject to ROSH. But these are things that it's really important that there's not a blanket legislation, because the negative environmental impact of preventing all that PV deployment would be catastrophic and much, much worse than the very manageable risk of having some toxic elements or rare earths like indium in these devices and technologies. Yeah, and then last question, because
just a quick question. Which countries would you say are leading PV technology in terms of first patents and secondly manufacturing?
So manufacturing is very easy, and if you're talking about existing technologies based on silicon, it's China, absolutely. There is a drive for new types of PV, as in sort of more advanced silicon, and there's a growth of a rebirth of European manufacturing, if you like. There's a number of companies with hundreds of megawatts of capacity going up to gigawatts over the next few years, for instance, silicon junction cells. But the Chinese manufacturers are also scaling up and probably much faster. So that's going to be challenging. There's thin film. There's one thin film company that's been very successful, that's First Solar. There hasn't been a second solar yet. They're in the US. They produce cadmium telluride. This is fantastic for gigawatt scale production, tens of gigawatts, but it won't be able to scale to hundreds of gigawatts and terawatts. So First Solar presently have about 80% of the world's supply of tellurium going into their product. So that one company has been extremely successful, possibly over the last 10 years, the most profitable PV company. They also deploy and do solar farms, and that's where they go. But they need a new technology, and that's where something like perovskite that's very scalable. So just as a comparison, the amount of lead in a perovskite film, a single junction, to produce something like 12 terawatts. If we were manufacturing 12 terawatts of perovskite PV panels, we'd use about 2 days of today's production of lead. So, small lead, 1% of today's lead production to produce more than all our power from manufacturing capacity of PV. That also gives you an idea of the potential environmental impact of it. We don't have to change. We're not putting more lead into the environment. We can just cut back a little bit on lead acid batteries, and that would more than give us all the capacity to produce these PV modules. And of course, there's the perovskite stuff. And I mean, there we do have we being Oxford University and Oxford PV, presently have the largest patent portfolio, and certainly one of the most advanced. We claim we're the furthest ahead in industrialization, but of course we don't know what everyone else is really doing. There's going to be quite a lot of competition there going to market. We're in a strong patent position. There are other patents filed across the world, distributed amongst other people as well. Okay, well, I think with that, thank you all very much.
Yeah, sure.
What's driving
When are we going to be able to buy?
Hopefully, I know, me too.
Well, I think they may be able to do more. In the UK, what drives it is the sites made available. Development. And then every few years they have an auction process. Where basically they will companies who have a site can bid for developing that site. And what they put forward is the price of power they're prepared to generate. And basically the lower the price of power. Yeah. So and that's their guaranteed price. So if the price of power in the future is higher, they get the higher price. If it's lower, then the government has to top it up. The government at the moment is setting pace. So the government could change the rate of pace by simply allowing more wind farms. They could allow more money to be given away in the auction process. At the same time, it could be the case that a company could look to develop a site without going into the auction process. Simply take the power price as it was. Obviously, that would be at risk then of if the price is too low in the future, then we may not make any money.
So even though these companies may not do it, maybe they have fine.
It's a financial calculation.
So in the African countries, they have absorbed the technology and build its own solar